Good morning. Good morning, everyone. Nice to see you all here. Thank you for coming. We're going to talk today about Android security and mobile chipsets, more specifically about Qualcomm's mobile chipset software. If you're anyone like me, then you're probably expecting some like juicy vulnerabilities, right? Actually, this presentation is a result of almost year-long research. And we're going to show you not one, but 4 vulnerabilities in Qualcomm's chipset software. Actually, these are not marketing slides. They're the real thing. We will walk you through some of the exploits. Hopefully, by the end of this session, you will be hacking each other here in the audience. So those who are afraid, please turn off your mobile devices. My name is Mordekhay. My partner here is Adam Donenfeld. We are researchers at Mobile Threat Prevention team in Checkpoint. And let's dive in. Well, this is a very casual slide. You have seen many slides like this, I'm sure. Android architecture, but I want to focus on the Android supply chain, actually. So Android is built on top of the regular Linux kernel with slight modifications. Google took it, added the Android open source project, and together they create the basic, like vanilla Android version that OEMs take and adapt it to their specific devices that they want to produce. Like Samsung, HTC, LG, many others, they add their modifications, they add their cool themed wallpapers, their revolutionary calendar app, the best in the market gallery, some other crapware. But there is a missing link in this slide, and it's the chipset. Chipset is the most important part of the device hardware. It's the CPU and the GPU and all the sensors and some other things too. It changes from device to device. And the chipset comes with software because the operating system has to communicate with the hardware, so they're device drivers. And they're created by the chipset manufacturer, and they're integrated in this process. Naturally, these are very low-level things, and the way low-level things work, once there is a vulnerability, you probably have all the system compromised. And the issue I want to stress here is what does it take to patch such a vulnerability? When we're talking about a vulnerability in a simple application like, I don't know, even Facebook, it probably takes Facebook a couple of hours to patch it, release it, and then phones just download it, update automatically, and end of story. Here, in the case of a chipset software, the chipset manufacturer have to fix the vulnerability. To do that, they have to communicate with the OEMs to make sure that it works actually for all the existing devices, it's backward compatible, or to decide that these devices won't get the patch and these will. This is both technical and bureaucratic process that takes a lot of time, and many times that's where the patch fails. That's what prevents the patch, this bureaucratic process. After they complete this part, they have to test it, the chipset manufacturer at his side, and then all OEMs for all the devices that they decided to patch. From our experience, it takes, like the fastest is 2 months to patch the first device, the first. And then it takes months to just spread to other devices. And in the end of this process, there are always devices that are left unpatched just because they're not compatible, there are not enough items from this device in the market. So in many cases, its vulnerability stays relevant for a long, long period of time. Now add to it this. if we're going to focus on Qualcomm now, and Qualcomm has 65% around plus minus of the LTE market currently. It's many millions of devices. So when talking about chipset and Qualcomm specifically, we have a very low-level component that is comprised of many, many parts, many internal models, like a lot of opportunities for bugs and vulnerabilities, a very logistically complicated supply chain that leaves these vulnerabilities open for a very long period, and a huge victim pool. So we didn't did an exhaustive search of all the components of the Qualcomm chipset software. There are really many parts, and it really sometimes felt that you just go in, you look for it, and you will find something eventually. So let's do the fun part. This is our Qualaland. We will start with a vulnerability that's called Ashmanian Devil. It's a vulnerability in the Ashmem model. Continue with the Koala root in IPC router, and then two vulnerabilities, Syncocca root and Kanga root in the GPU model. So the first vulnerability is Ashmem, Ashmanian Devil. Ashmem is a standard model in Android. It's not a Linux model originally. It was something that's developed by Google to improve memory management in the Android system. It's similar in a way to a regular shared memory in Linux. It's basically a file-based API that works using file descriptors. I hope someone understands me. So Qualcomm, they took this existing Google-created model and added to it some APIs to add some functionalities they needed for their models. And we're going to look at this function, switch to code reading mode. Now it will be really code and functions and pointers. So we have this get ashmem file function. That's really a simple function. It receives a file descriptor and returns some internal data that is associated with this descriptor that is otherwise not available to the user. We get the file structure from a file descriptor, this one that we get here, and then just check whether this file is actually an ashmem file, because the file descriptor can be any file in the system, and they wanted here to give a functionality only to ashmem. So they check if it's an ashmem. If it is, then return some interesting stuff. If not, just return nothing. So it is a really simple function. I don't think there is some interesting way to attack it itself. But as researchers, we have to look at it critically and ask ourselves, how do we actually check that the file is an ashmem file? The by-the-book approach to check a type of the file is actually a little bit complicated. You really have to go inside the structure that is addressed by the file descriptor and actually check that all the file operations that are listed there are file operations for the file type that you actually want to get. For example, the file operations, this is read, write, close, poll. So you really have to go there and check that is read actually ashmem read? Is write actually ashmem write? Is poll is actually ashmem poll? because it can be theoretically anything. It can be socket read, socket write. So that's the by-the-book approach, and it is complicated. You know, you have to compare pointers, and I understand them. They decided to take a shortcut. They just assumed that if a file is called hashmem, then probably it's an hashmem. What else could it be? Okay, so we see it and we feel like, okay, now it's so easy. Let's just exploit it right away and get those escalated permissions. So all we need to do is just create a file and put it in root mounting point. But we cannot do that because the root mounting point is read-only. Moreover, other root mounting points are read-only too on Android. And if anyone thinks about SD cards, it's a symbolic link, so it won't help. We're not screwed. There is a solution. Long ago, in a land far, far away, when Android was young and reckless, when probably nobody of us was alive because it was like 3 or 4 years ago, Android market didn't allow applications larger than 100 megabytes to be stored and downloaded from the market. But there were applications, mostly games, that required much more than 100 megabytes for all the textures and, I don't know, all the stuff they do there. So Google created a way to solve that problem that is called opaque binary blob. Actually, like the name itself, when I read opaque binary blob, I think about, oh, it must be some like Dread Pirate Rogers or something. Opaque binary blob is a way to create your own file system, to download a file system from your own server, to mount it for yourself. It's like really for personal use only, and then there can be all the extra data your application needs, and use it as usual files. It's really for the application, it's like usual files for that matter. And since it's private for the application, it doesn't require some permissions. It's really like, it's naive and nothing bad can come out of it. But since in our chipset code, they decided to just check the file name and not check on which file system it is or things like that, all we need is just to create an OBB, put there the file with all the internal data that we want to point it to all the interesting places that allow us access to all the interesting stuff, mount it, and use the API. And the device is ours. That was the hashmem, and it was not the most interesting one. For the most interesting one, I would like to ask Adam Donenfeld, as actually the mastermind behind this exploitation.
Can you hear me good? Great. So going on to Qualroot. Okay, so Qualroot is a vulnerability in the IPC mechanism of Qualcomm. It's simply a new address family in the system, like any other socket. And it reminds the average use of IPC mechanisms, except that it has a few interesting features. For example, as a socket, I can whitelist or blacklist other endpoints in the system based on their group IDs, for example. And another cool feature which we're going to focus on is that I can monitor creation or destruction of new sockets in this address family. Another thing about it, obviously, it requires no permission to use that. So there are 4 types of this endpoint, of this socket. We are going to focus only on client ports and control ports, mainly because the 2 others require high privileges to use them. So every time you create a new socket, it is by default a client port socket. Now, a client port socket is a socket that can communicate with other sockets. It can send and receive messages in this address family. Now, control port is a different type of socket. We created almost in the same way, but control port cannot communicate with other endpoints. It will only receive messages for creation or destruction of new sockets in this address family. So how do we create a control port? We just have to ioctl our current client port socket. So as we can see here in the function first locks our client port socket, so we cannot issue 2 ioctls simultaneously on the same socket in the same time. And then according to our request, it issues specific operations. In our case, if we issue IPC router ioctl bind control port, our client port will be converted to a control port. Now, how is the conversion actually done? So for each socket, there is a list. So there is a list of the client ports, and there is another list for the control ports. And the conversion is basically taking a socket from list A and putting it in list B. So the actual conversion function, for those of you who are not familiar with the Linux API, this function locks the client list. We have to do that because we want to prevent race conditions or modifications on the list while reading it. Then we take the object out from his current list, which is the client port list. Then we unlock the client list. We lock the control ports list. We add the object to the control ports list, and we unlock the control ports list. Seems pretty straightforward, and yet this function is vulnerable. So now let's examine step by step this function to see if we can find the vulnerable code. So the first instruction locks the client list. Then we take the object out from his list. And then we unlock the client list. We lock the control list. We add the object to the control list. And then we unlock it. Seems pretty straightforward, and it looks okay, because so far it was indeed okay. What happens then if we try to convert a control port to a control port? That's perfectly okay with the system. At least this was before the patch. So we lock the client list. We take the object out from his list, which is not the client list. We unlock the client list, and we do the same, lock the control list, and we add the object here. So as you can see, although we lock the client list, we modify the control list, which is not locked. And that's a tricky situation. So we're up to something here. We can modify the control ports list without a lock. So we can delete 2 objects simultaneously from the list. And therefore, we have a race condition situation here. And now let's see what happens when we actually remove 2 objects simultaneously from the list. So that part is a little bit hard to follow. Here we can see the API in the Linux kernel that handles removal of objects from double-linked list. We are going to remove A and B here. We will first work on A. So we can see here more information. If you miss something, you can just look at the pseudocode here. As you can see, for example, here we take A is next, which is B, and we set B's prev to be A's prev. So B's prev equals control ports. Now, since there is no lock on the list, there might be a context switch. And now we're going to remove B while preserving the modification that happened on A's context. So we take now B's next, which is C, and we set C's prev to be B's prev. So C's prev equals control ports. Now going to the next instruction, we take B's prev, which is control ports, and we set control ports next to be C. So control ports will now point to C. Now finally, B will now point to the poison values, and it is effectively removed from the list. The memory is also freed, so it can be reclaimed by spraying the kernel heap. And now going back to A to finish the process, we take A's prev, so control ports, and we set its next to be A's next. So control ports next equals B. And finally, A now also points to the poison values, and it is removed from the list. Now, obviously, it's not a valid double linked list anymore. So let's remove all the unused objects from the list. And we get something interesting here. So the control ports list now points to a free reclaimable data. We using just spraying just any. We have a lot. Okay, there are a lot of ways to spray the kernel heap. We chose Unix diagram, and we managed to reclaim it. We managed to fake this object. Now, once we fake the object, we want the system to use it. Now, since this is the list of the monitoring objects, all we have to do to get the system to use it is just create or destroy any endpoint in this address family. So by closing a client port, the list will be iterated. Now, each time the list is iterated, a function called postPacket2port will be called on each object. Now, here we have a lot of new opportunities. I think there is at least one more way to exploit this vulnerability, another way to exploit it. Here you can see this is our object. So there are a lot of primitives from information disclosure to function call primitives to memory corruptions, and I think there are even more stuff. The path we chose to exploit it was using wake up. So what is wake up? Wake up is a macro to another function called wake up common. So here you can see that we control we have 100% control over the content of the first argument, and therefore we can control queue. Now, if you control queue, we can also control task list. So this entire iteration will be done on our fully controlled list. So therefore we control cur. And if we control cur, we have a new primitive. We can now call any kernel function while controlling most of the first parameter. Now, for those of you who ask, why don't we call a user mode function? That's because we want to bypass PXN or the ARMish SMAP. So a new primitive, a function call to any kernel function while we control most of the first parameter. Now, the most convenient way to continue from here is calling a function called commitcreds. For those of you who are not familiar with this function, it's a Linux kernel function that receives a pointer to a credential struct, and then it just sets our credentials to be the ones we provided as a parameter here. So we can just pass root credentials and we can get root. But it's not, our current primitives are not good enough. Why is that? As we can see here, func is derived from cur. Now, if you want 100% control over cur, so we cannot really call any function we want. And if we want to get the fully available capabilities on the system, we cannot control it. So we need to upgrade our primitives to get 100% control of the function. So we have to find another function that by controlling just a little bit from its first parameter, we can get another primitive of a function call, but now we want to control 100% of the first parameter. So we found a good candidate. USB read done work fn is a function that receives a parameter. Now, since there is a container off, we really have now 100% control over the interesting stuff in CH. And if you control CH, we also control rec, because this is a pointer, and rec is derived from CH. And now, combining these two variables together, we get a new primitive. We can call any kernel function we want while we control the pointer of the first parameter. And now we can just we have 100% control over the first parameter. Actually, over the first three of them, but we just need the first one. So now every time we want to call a function, first we're going to wake up common, because that's a function we had in post-packet port. Then we go to our gadget, USB read done work fn, which eventually allows us to call any other kernel function in the system while controlling 100% of the first three parameters. And now we have sufficient primitives to screw up the device and get ourselves root capabilities. So again, the exploitation flow. There is a doubly linked list of the monitoring endpoints in the system. Each time we open or close a socket in the system, the list is iterated. So now using the vulnerability, we want the list to point to a free reclaimable data. So once we did that, our next step is to spray the kernel heap to reclaim this data. Again, we used Unix diagrams, but I'm sure there are other convenient spraying mechanisms to help you with that. So once we did that, we have control over the object, and we want to point back to the beginning of the list to prevent situations where iterations will crash the system. And now we want the system to use our fake object. So we just have to create or close any endpoint in this list, in this system. And then it uses our fake object. And then it starts our fake chain of function calls. So first it goes to wake up common, then it uses our fake task list, and eventually it starts to call some functions. So the first function we called was qdisk list del, which cleans up the control ports list. This is mandatory to prevent the list from being corrupted, and if there will be any legitimate use of the list, the system won't crash. The second function we call is enforcing setup, which effectively renders SLLinux useless because it will now be permissive. And finally, we call commit creds, and then we have roots, and we have the full capabilities available on the system. So we won. Now, demo time. I'm sorry for the Windows, it was just for the recording. So now we're installing our routing APK. Now, we're going to see that the Linux version is indeed a legitimate version that comes with a ROM that Google supplies. We're going to see, I hope you can see it. We're going to see that the device is actually a Marshmallow version Android. We're also going to see that the device is not rooted, and that we are actually not root. And also, we can see here that SLLinux is currently enforcing, so this mechanism, at least back then, it was available for any unprivileged application. Now, our exploit, eventually, the payload can be changed, obviously, but the payload we chose was first placing a suid file in the system partition, and also we set up a service on port 1337. It's a netcall service. We just can connect to this service, send text commands, which will be issued as root. So now we are going to see that the system partition there's nothing special in it. We're going to, and that our service in 1337 is currently not available. Now, in the system partition, there would be a file called zugang, which is accessed in German, and that's going to be our suid file. So now we are going to actually exploit the vulnerability. So we're going to see some logcat crap. It takes approximately 3 seconds to exploit the vulnerability from the point of no permissions till you are root. Because I didn't invest too much time in the GUI, we have to wait like 5 more seconds. So at this point, the exploit is already done. And now we are going to see that we are still not running as root, but SLinux is no longer forcing, it is now permissive. And if we try to netcat to our ROA237 service, we're not going to get connection refused anymore. And if you read the system now, we see that there is a zugang file, which is a suid file. We're going to read fstub, which is only accessible to root users. So we're going to see that we are actually root. And by issuing the ID comments, we are root, and we have the full capabilities available on the system. And that's the demo. I hope you liked it. So now going to the last two vulnerabilities in our Koalend roadmap. The last two are in the GPU module, syncockerroot and kangaroot. But before we speak about syncockerroot, we have to speak for 30 seconds about a mechanism called IDR. So IDR is a Linux kernel mechanism. So in fact, it has nothing to do with Android. I mean, Android used that, but it's not something that was introduced in the Android vanilla. Now, this mechanism helps with it allows user mode to reference kernel objects without revealing sensitive kernel addresses. So let's say that the user creates a kernel object. It asks this kernel to create an object. Now the kernel allocated data, initialized stuff, and now we have a kernel pointer. Now obviously we don't want to give the user any information about, we don't want to give the user this kernel address because that would be an information disclosure. So instead the kernel passes this address to the IDR mechanism, which maps between this address and between a number. And instead of giving the user back the kernel address, it returns the user this number. And now every time the user wants to use this object for updating, for destruction, for whatever, it will give the kernel this number instead of the address. And with this in mind, time to introduce you to syncockerroot. So syncockerroot is a vulnerability in an object called syncsource. The object is used to synchronize between the GPU and the currently running applications. Applications don't use it themselves. It is usually wrapped by other graphic engines like OpenGL and soon by WebGL 2.0. And now we don't have to know a lot about this object to understand the vulnerability. All you have to do is knowing how to create and how to destroy them. And this is done by issuing two ioctls, ioctl kgsl syncsource create and destroy. We send them to the kg to /dev/kgsl 3d0 driver, and they are referenced by the IDR mechanism that we saw before. So that's a function that destroys this object. It's pretty straightforward. The user controls data, and therefore it controls param and param ID. Now data is sanitized very well, so we didn't really look into that. We did, but we didn't find anything interesting. Now, here we see, we fetch the ID from the IDR table, and then if the syncsource object exists, so we drop the ref count twice. One for the creation of the object, and another one, and again, because this function increases the ref count by 1. So how does it actually look like? The ref count starts with 1, then this function increases it to 2, then the ref count is dropped once for the creation, and it is dropped again because this function took a ref count also. And here the object is actually destroyed. But something is missing here. There is no check that the object is about to be destroyed. So what happens if we call this destroy function on two different threads? So we have thread A, and we have thread B, and they're both calling this destroy function on the same object. So first, thread A increases the ref count by 1, and then drops it back. Now there might be a context switch. Thread B increases the ref count by 1, and then drops it back again. Now, going back to A, the ref count is dropped to 0, and at this point, the object is actually de facto freed, and it can be reclaimed by spraying the kernel heap. but B is not done yet. So at this point, we can spray the object, we can do whatever we want, and B will drop the ref count again, either to -1 or either our new object to 0. And then we might free another object. So again, first we create a sync source object, we get an IDR number, we issue a destroy request on these two different IDR numbers, on this same IDR number, sorry. And then the ref count will be dropped to -1. Before we get to -1, we can spray the kernel heap, and we can cause it to free our new fake object. And therefore, we can do interesting stuff. And then we have a double free, which is de facto we can get to a use after free situation. So that was in Coca-root. Now finally going to Quadroot. So Quadroot is a vulnerability in the main GPU wrapper module. It's actually the module that connects between the user and the GPU hardware drivers. So users can map user data to the GPU. There are a lot of ways to do that, mapping user addresses, mapping files, mapping hashmem. We just have to choose our method. And each time we do that, an internal struct called KGSL mem entry is allocated, and it contains a lot of important data about our mapping. It controls the protection of our mapping, the ref count, the actual address, and many other important stuff. Now, the mapping is referenced again by the other mechanism. So the first thing we did was going to the destroying function. As we can see, that's the internal structure I told you about. Again, using the other mechanism, we check whether this entry exists, and if it does, we free it. So we were super happy because we thought, okay, maybe they were wrong again. But surprisingly, this function was very well written. It atomically checks whether the object is about to be destroyed, and if it is, then if it's not, it will be dropped, but for the next destroy call, it won't. So this time, I did it almost perfect. So we went to the function that initializes this data. So this function is called after every map request. It receives a block of uninitialized data, KGSL mem entry, and then it associates it with an IDR number, and it initializes it. And there was a problem, because after this point, this object can be referenced, even though it is not initialized yet. So let's see the legitimate use of how we should use this API. Thread A allocates this code is done in the kernel. So the kernel, thread A allocates data, but it doesn't initialize it. Then it associates it with an IDR number. And then it initializes the object. Now, the releaser thread checks whether number 6 exists. If it is, it passes the check, and then it frees the data. Now, obviously, it's a matter of context switching. What happens if thread A allocates data, and now we know that our last object was number 5, so here it will, for 100%, will be number 6, because that's how IDR works. And once we associate it with an IDR number, it is now inside the IDR items, and it is therefore can be referenced. So now we can already ask, even though thread A didn't done yet, we can already ask for the destruction of IDR number 6. And now, since the object is already associated with an IDR number, we can pass this check, and number 6 will be freed. But since thread A did not finish yet, it will now initialize free data. So we have use after free here. So again, how to do that? First, we map some data to the GPU. We get the IDR number. We know what's the next IDR number we're going to get. then we are just asking to map more data, but in the same time, before the thread returns, we also ask to free this data, and thread A, the thread that allocates data, will use free data. So there is uses for free situation on the entry parameter in function kgsl mem entry attach process. So that was Kangaroo. Now regarding the disclosure. So we disclosed Syncroot back in April, and it went pretty well. We gave them for each vulnerability, we gave them a 3-month embargo, and for Syncroot, it was pretty good. For Kangaroo, Qualcomm was also responsible. Actually, Qualcomm was very collaborative, and they were very good with the timings. But for some reason, Qualcomm released a public patch, but only a month later, Google deployed their patch. So for 1 month, the vulnerability was actually public and unpatched. Now, for Rashmanian Devil, even though we reported it to them in April, it is still not fixed by Google. So congratulations, you're all vulnerable. But still, a lot of different OEMs worked with Checkpoint, and we instructed them what to do, and they issued out-of-band patches for that. But still, at least as we know it now, up to now, all the Nexus devices are still vulnerable. Now for Qualcomm, although we reported it back in February, and even though you saw a very basic way to exploit it, it is still not fixed by Google, and not just by Google, by most of the OEMs. The way they fixed it is by setting an SE-Linux rule that blocked access to this mechanism. But you should know that it doesn't fix the problem. If you find a vulnerability in a process that has access to this mechanism, you can exploit it, and you know how to do that now. So they still didn't fix that, even though it's been months since then. Now, I hope the disclosure will be more convenient in the future, because it wasn't good. It was actually bad. Now, suggestions for the future of the security of Android. So commit creds, I'm not gonna say pay more attention to your code, because I want to give actually concrete suggestions. So for more than a decade, commit creds was an extremely convenient function for exploits. Even though from a design point of view, it might sound funny, this function should be hardened, because all we need now is a function called primitive, and we are done. We are root. So, and there are functions that are already hardened. For example, Cisco reboot requires you to put specific magics to call that. So I'm sure this function can be changed, because right now, that's all you need to exploit a Linux kernel vulnerability. My second point, so ASLR is not a new concept. iPhones have it for years. The Linux kernel already have it. The Linux kernel that run on desktop endpoints. And yet, for some reason, Androids still don't have it when it comes to the kernel part. Now, I think that's an extremely important feature. If you would have it, it would be much more complicated to exploit Qualcomm. But because of the absence of this feature, it wasn't so hard. Finally, SE-Linux. So SE-Linux is a great mechanism, and it made the attack surface much more smaller than it was before. And yet, if you have a mechanism but you don't know how to use that, it's not good. It doesn't work it. And if applications had access to the Qualcomm's IPC mechanism, so what's the point of the mechanism if you don't put appropriate rules? Now, with that said, the overall current mitigation status in Android is fairly good. PXN, or the SMAP for x86 users, which was introduced 2 years ago, made exploits in the kernel much more complicated, and yet a few missing components, a few components are missing to make the situation much more secure and much more safe. Now, Checkpoint created an app that checks whether your device is vulnerable or not. The device actually tries to partially exploit the vulnerability. So it can tell you whether your device is vulnerable or not, but there is no risk of breaking your device or rooting it. You can enable it if you want to check if you are, if you are vulnerable or not. And that's it. I hope you liked the presentation, and if there are any questions, that's the time.
Any questions from the floor? No?
Not anyone at the same time?
No, yeah, no rush.
Well,
if you have
we're
any,
still here, so.
yeah, you'll be here throughout the whole day. So
Okay, so we're here on if anyone wants to ask some questions, and thank you.
All right, thank you very much.